Hey, Pamela.
Hello.
Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We'll get to that. So for those of you who have no idea what it is that you stumbled into, this is a live recording of Astronomy Cast, our weekly podcast about space and or astronomy. And this week, we are going to be starting a brand new series on what we both thought was just a super clever idea. And this is, we're going to be talking about really cool experiments. So we always talk about like how we know what we know, and we, blah, 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 the dark matter experiment, dark energy this and such. But we're going to go even deeper, and we're going to spend a whole episode talking just about one experiment, which either helped confirm something or weirdly helped unconfirm something, which is what today's episode is about.
I like it when you make up words.
Yeah. Or we disconfirm something. So this is a great example. This experiment is great because it took.
There's a word for it. It's just prove something. But I forgot because your made-up word is so awesome.
Okay. So this is great because we're going to talk about an experiment that astronomers legitimately tried to, or physicists legitimately tried to detect something that should have been there, and it totally made sense, and yet it wasn't there. And by figuring out that it wasn't there, they had to go back to the drawing board, and some Einstein came up with a better idea. So we'll get on to that. So if you want to ask us some questions while we're doing the show, feel free. The way to do that is using the Q&A app, which I have enabled, and just to prove, I will say hello to some people. I'm going to say hello to Nancy Graziano, James Oliver, Michael Daumer, Guido Bibra, Nuno Lunca, Hugo Burnham, Steve Eskison, Ed Thompson, Sev Dustbunny, Richard Clark, Giselle Sabarin, Patrick Calhoun. Yeah, so those are the people who jumped in early into the Q&A app and said hello or posted a question. So go ahead, post a question, and I will either try to incorporate it into the show as we go, or we'll stick around afterwards and we'll answer your questions about space and astronomy, either the topic of today's show or any topic you want to talk about.
Steve Eskison already has a pretty daunting question in there.
Nice.
2 points for me that I don't know how to add from my side of the question and app, and the Q&A app.
Okay, great. Well, I can't wait to confront you with that question then. Get doing some research.
Right.
Okay, great. Any reason why we shouldn't begin this episode?
No. Shall we press record?
Let's do it. I'm ready.
Okay, I've pressed record. Hi, Preston.
I've also pressed record. Hello, Preston. Enjoy this astronomy cast that we are about to make for you. All right, here goes. Astronomy Cast, episode 368, Searching for the Aether Wind, the Michelson-Morley Experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I am good, but I have some sad news to report, which I don't know if you heard this. Tammy Plotner, who was one of the longest time writers for Universe Today, passed away last week.
Oh, no.
A long struggle with MS. And so Tammy joined Universe Today back in like 2004, and she was really the first freelance writer that I ever hired, and she just did tons and hundreds, thousands of articles over the course of her work with me, including a fantastic series on the Messier objects, all the constellations, and which she was trying to turn into books. And she did a What's Up 2006, What to See in the Night Sky Every Night for 2006, then again for 2007. So she's just really infectious amateur astronomer, taught me a ton of stuff, and it sucks that she passed away, and so she went offline for periods of time, and then we just heard from her local astronomical society that she passed away. So I just want to thank Tammy for all the work that she did for both astronomy and for us personally at Universe Today. She's really going to be missed. So, let's move on with today's topic. So waves move through a medium like water or air. So it seemed logical to search for a medium that light waves move through. The Michelson-Morley Experiment attempted to search for this medium, known as the luminiferous ether. The experiment gave a negative result and helped set the stage for the theory of general relativity. So we are going to be starting a new series, not sure how long this will last, where we are going to talk about pivotal experiments in space and astronomy that really helped change the way we look at the universe. And this is one of the biggies. So set the stage. What before this experiment was performed, how did astronomers think about the universe and the medium?
Well, it wasn't just astronomers. It was the entire field of natural philosophy, is what they called it back then. There was the understanding that sound requires a medium to move through, and as it goes from one medium to another, its behaviors change, its velocity changes. It was understood that light also passes through stuff, glass, things like that. We saw how it refracts through prisms, and this seemed like it was behaving a lot like sound. We also know that you can raise waves in liquids and semi-solids. I don't know what you refer to as a string, but you can make strings and guitars vibrate. These are waves moving across the string. And again, as the wave goes from one medium to another, its properties change. And so it was figured we have waves moving through bodies, which now we call sound waves. We have actual sound waves that our ears hear that move through the air. And so it was assumed that there had to be something that also allowed light waves to move through space, and that was in part responsible for how light changes the same way sound does.
But how did astronomers, or how did scientists, physicists know that light acted like a wave? What kinds of behavior had they seen that told them that it was a wave?
The first thing that was noticed was things like interference. So you can take light and you can, by putting it through slits, by causing it to interfere in different ways, you get these patterns that resemble the same sorts of patterns you get when water waves pass through, well, slits in a breaker wall. And so we saw this wave-like behavior with diffraction, interference, and this seemed to be a very wave-like thing to do. It made sense, but light, unlike water waves, also showed particle behaviors with the way it reflects off of things. And so there was this wave-particle argument that passed through history that I believe we've done episodes on way back in the first 100 episodes. This wave-particle duality led to a lot of confusion and a whole lot of, I'm just going to ignore the fact that this is two things at once and only deal with one part at a time. And it's that only dealing with one part of the problem at a time, only dealing with it as a wave, or only dealing with it as a particle, which is admittedly part of, you can only observe it as one or the other, so pick one. But this thinking of it as only one or the other is part of what led to the making up of the concept of ether.
Okay, so what did they think this ether was?
It largely goes back to, actually, in some ways, how Newton was thinking about it. You have water, when you look at the way it interferes with things, the waves are generally, the waves are bigger than the particles of water. When you look at how sound waves move through the air, the sound waves are bigger than the particles of air. Well, light waves are pretty darn tiny. And so as we got better and better understandings of light waves, it was supposed that the ether had to be something that was smaller than the light waves. So we knew it was going to be hard to detect. And I have to admit that in studying for this episode, it actually made me go, how the heck did we figure out there isn't air in outer space? This is one of those questions that never previously bothered me and now deeply bothers me. Because while we understood from mountain climbing first off, and then from the gas laws that were developed in the 1800s, that the pressure of air decreases with altitude, I have to wonder why they didn't just suppose that the ever so diffuse nature of air might allow waves to continue to move through space from stars and such. More things to look into, evidence that we don't know everything, or I don't know everything, or both, probably both. But in order to try and understand light, they knew air wasn't enough. The particles of air are way too big. Therefore, there has to be, they thought, something else, something smaller than air. The luminous ether that allowed the luminous light to travel through space.
Right. Okay. So some kind of particle, some kind of dark matter that they didn't recognize. I know. Completely different. Some sort of dark energy.
Stop with the misconceptions.
All right. I'm just gonna, because the people are gonna go there already, so I just want to go there before them. Okay. So there was some substance. It was water. It was air. It was the ether. And it was everywhere you looked, not ether like the drug, but ether the
yes,
written with an A. Okay, so this is great, and so you've got this thing, and so then I guess what was the hypothesis, right? What was the experimental that they set up to say, well, if this ether exists, we should detect it by doing X?
So if you start looking at the equations for interference, you realize that the distance that light travels is one of the most important features for setting up how the diffraction pattern will appear. And one of the things that really matters is when you're combining light, you have to have light that's what's called collimated. This means all the wavelengths neatly line up. So when you're shining that collimated light at a slit, you have light that goes into the slit with all of the light waves lined up, and then based on the different distances that light travels from those two slits to wherever you're focusing the light, you end up with your highs and lows in the amount of light observed. So once that was figured out, and that's a fairly straightforward experiment to do. In fact, it's one you can do at home with the laser pointer you use to torture your cat. Take a couple of razor blades and make a very thin slit, and you can create a fringe effect on the wall. And if you get fancy with a piece of aluminum foil and putting some slits in the aluminum foil, you can create that double slit and shine the laser beam on it, and again see, in this case, your beautiful interference pattern on the wall. We knew that, and so Michelson got to thinking, well, if we start thinking about how to measure the speed of light, if we start thinking about how things are going to get affected by this motion, if we start thinking about what we observe with sound waves, which are easier to deal with, we know that sound waves, you have to take into consideration the velocity of the source, the velocity of the observer, and the medium that they're in. When you're dealing with light, you just look at the differential effect. When you look at light, you can deal with frequency and wavelength using standard equations. It's not that hard. But having to deal with that medium suddenly makes everything much more difficult with sound. And they went down the much more difficult track originally and came up with this really awesome experiment. And this awesome experiment was, if you take a partially silvered mirror, one that reflects some of the light that hits it, but lets some of it transfer through it. Essentially a one-way mirror like you have in police stations on television.
Like a beam splitter glass.
Beam splitter glass. This partially reflecting, partially transmitting glass will take the beam of collimated light that you send at it, send some of it to one mirror, send some of it to another mirror that is at an angle away. And if you put these two things at right angles with that partially reflective, partially transmitting mirror at a 45-degree angle, so basically take a box, put a mirror along the diagonal of the box, and put a light source on one side, put a detector on the adjoining side, and make the other two sides mirrors. Well, this is a situation that allows you to start combining light that, if there is any difference in the medium, the physical identicalness of the distance the light travels going to both of those two reflecting mirrors will not be the only thing that matters. That speed of the medium, in this case the ether wind, the luminiferous ether wind, will cause a path length difference.
Okay, so let me see if I understand this correctly. So they took the light, they beam split the light into two separate, possibly equal-ish beams of light, but they came
Physically
from the same
equal.
source.
Yes.
Right? And then you can then play with the two halves of the light, which started out with the same source, to do things like make them go down longer paths, make them go down, maybe make them go in different directions, one which is in the direction of the, and I'm putting some air quotes here, the direction of the wind that you think it might be, and then the opposite direction of the wind or perpendicular to the wind. But then you bring those light paths together and see if you get any change in the way that they interact with each other via the double slit experiment again. So you're looking for changes in interference patterns purely based on what you've done after you've split up your light. Is that right?
You made it a whole lot more complex. You were basically including the definition of a Michelson spectrometer, which we use in astronomy to basically do imaging spectroscopy. What they did was a lot simpler. They literally had a big old stone slab working out at Case Western Reserve University, and they had two reflecting mirrors that were at right angles to one another, one of them in the direction of the Earth's motion, one of them away from the direction of the Earth's motion, and they could rotate this entire thing, but the mirrors themselves were fixed on this stone slab. They had in between this at a 45-degree angle to both those mirrors, the transmitting, reflecting mirror, and the idea of having everything fixed was, if everything was fixed, then the only difference in travel path would be if it was due to the ether. And one of the things they did, which when I read this just sort of made the parts of my brain that have done interference experiments go numb, was they were doing this with white light. Earlier I said, do this with your cat's laser, your dog's laser, whatever you use. I've heard you can actually get betta fish to chase laser pointers. That single colored laser pointer you use, whether it be red or green or whatever color it is, that's really easy to create an interference pattern with because it's only one color of light. With white light, you have to worry about the path length for all the colors being the same. You have to worry about there being nothing at all that varies across all the different wavelengths. This means that you have to start worrying about surface properties, a whole lot of other stuff.
Like just the glass itself is gonna diffract and reflect the different colors of photons by tiny different amounts, right?
Well, mirrors are pretty good. They don't actually do that, but you have to worry about, is it truly a mirror where going through the mirror, it's hitting at an... It's complicated, but chromatic aberration isn't the same sort of chromatic aberration that we're used to dealing with lenses that are bent and you have different path lengths through the lens. The path length through the glass, as long as the glass thickness is consistent, is going to be the same. Anyways, it's really stupid complex.
Yeah.
And when they were doing this, they found that they could get that perfect alignment that comes from both paths being identical. And they didn't expect that. They didn't want that. That meant that their result didn't fit any of the theories, which is the most uncomfortable place you can be as a scientist. There's really nothing worse than saying, I just did an experiment that proved that all of these people who came before me were wrong.
Right. Null hypothesis, right? They null result. They search that if everything had gone well, they should have figured out the direction the Earth was moving through the ether. They should have gotten a sense of like what its particle size was, density. They should have been able to verify all kinds of theoretical models for what this stuff was.
With their particular experiment, they were pretty much limited. I mean, particle size wasn't something they were getting at back then, but they were definitely going to start being able to say what is the rate of the I can't say the word. What is the rate of this ether that affects light that the Earth is moving through? How does it create a drag? What is its drag rate? What is the angle of its motion relative to the Earth? They were looking at all of these differential velocities.
Right, and you could get some deeper thoughts, right? Like literally, what direction is the Earth moving through the universe?
Yes. And when they did all of this, it came back to 1 part in a lot, we don't see a velocity and can pretty much rule out the Earth's motion as showing up in the data. And there were things that they saw, and this is something that I think we're actually going to go into in the next episode. The work that they did, they had to start taking into account actually the Earth's velocity, because things do contract along the direction of velocity. So it wasn't that they saw an absolute zero. It was that they saw something, but they saw something that didn't match any of the prior ether theories. And it was Lorenz who came along and looked at their results and started to figure out Lorenz contraction. This is what later went into the theory of relativity, where we talk about contraction along the direction of motion. This started to crop up in their results. It led to Lorenz. Yes.
That's crazy. I didn't know that you were starting to see these relativistic effects of the Earth's motion, and that showed up in the calculations that they were doing.
And this is where, because they used white light, they were able to see very fine differences in path length that occurred between the two right angle path lengths that the light went down. And so here's where we start getting a test that would later, with better and bigger and finer versions of the Michelson-Morley experiment using what are now called Michelson interferometers, we've been able to start, eliminating the fact that there might be ether. No, there is not ether. People who keep trying to blame dark energy on the ether. No, there is not an ether. We've pretty much disproved ether, but while we've gone on to do so much more in terms of looking at Lorenz contractions and starting to find amazing new ways to do one wavelength at a time spectroscopy using interference filters and Michelson interferometers.
So they should have gotten the Nobel Prize. I don't know if the Nobel Prize existed then, but should have just started up around that time.
1887. So.
Yeah. So they would have gotten their Nobel Prize. I don't know if you get a Nobel Prize in null detection, but so let's talk about how this sort of laid the groundwork then for. I mean, you started to go into this, right? Lorenz contractions. They started to realize that there seemed to be contraction in the direction of motion that the Earth was moving in. How did that feed into Einstein?
Well, I was planning to get to that in a few more episodes, but we can give hints of the future here. So first of all, this created the rather large problem of suddenly light didn't have a medium to go through, and expletive, Light is a wave and a particle, and apparently doesn't require a medium. And what is this strange thing that we're interacting with? So their experiment, which they managed to get published, which is always hard to do when your results don't match theory, their published results basically took our understanding of particle physics, not particle physics, rather, it took our understanding of the particle of light and the wave of light and broke it and forced us to rebuild it, not quite from scratch, because we did have a lot of experimental data, but the theories that we used had to have new things placed into them. It made understanding of the Doppler effect of light way easier, because suddenly it's much simplified how you deal with frequency and wavelength, much less ugly. But other than making the Doppler equations when you're looking at wavelengths instead of frequency much less ugly, it did create this whole, well, what do you do without a medium? And Lorenz got it part of explaining the experiment, and it would have to wait until Einstein came along and started trying to figure out the, well, energy aspects in many ways of light, that all of the answers would come out.
I'm assuming that this fancier and fancier versions of this experiment were then performed. People tried to get at it with more detail. You know, I mean, we have a sort of a similar situation, right, which is that people were searching for the Higgs boson, couldn't find it with the scale of the particle accelerators that they had available, but it didn't mean that the Higgs boson didn't exist. It just meant that the particle accelerator wasn't up to the task. And finally, when the Large Hadron Collider was created, it was able to generate the kinds of energies required to turn up the Higgs boson according to the standard model. So it's strange to me. I don't know. I mean, how did the theory go? Like, when they released their result, everyone would go, "Well, that's it for the Aether idea."
Now, everyone tried to replicate the results to prove them wrong, as one does, and that's part of science. I actually totally get behind the idea of saying, "Well, we're not sure about this. Let's replicate it," because there's a lot of research out there that when you try and replicate it, you can't. If you look at the amount of data on health studies and such that couldn't be replicated, it's really disturbing. But they had an experiment that could be replicated over and over and over again. And people continue to replicate it, continuing to look for signs of the ether at smaller and smaller scales. So by 1955, they were using quartz clocks and cavity resonators, and were able to eliminate our motion through an ether down to the scale of 3 kilometers per second. This has today continuing to use, now they're using Fabry-Perot resonators. They're down to less than 1 part in 10 to the minus 17th of the Earth's motion. We can't detect it.
Right, but that's great that this experiment continues to be done. It's like every time someone comes up with a much better method of splitting light or calculating the wavelength of light or with more precision, they run that experiment again at the next order of magnitude, just to be sure, which I think is just great.
And as one of the reasons I came down so firmly when you were like, dark matter, dark energy, is because there are people using the word ether to try and explain dark energy, and this is causing people to go, I wonder if actually just saying a word triggers ideas.
Yeah.
And so there is this, well, I wonder. And
well, one of the terms that's been used to explain what dark energy might be is this idea of quintessence, which sounds kind of similar to ether when you sort of roll these around in your brain, and it's, again, quintessence is both a nonsense theory from hundreds of years ago, but then a legit term that certain theoretical physicists are using to try and wrap their heads around dark energy. And it's a perfectly legitimate model for how dark energy works. And the problem is you pull one of these terms up that already has problems from ancient times, you're taking your, it's got to be careful.
Yeah. And this is definitely a very troubling situation where it's so easy, because of the flexibility of the English language, to take words brandished because they sounded cool by scientists and make inappropriate connections.
Yeah.
Dark energy has nothing to do with the electricity running through your walls. It is not going to save any energy crisis here on Earth. Dark energy and quiescence has nothing to do with the poetry of the past. These are modern ideas that we lack a new language to articulate. Once upon a time, black stars was a word. Now we use brown dwarf and cold white dwarf, depending on the language. Language changes, old ideas get lost. Unfortunately, language doesn't necessarily eradicate the old ideas.
Right. Cool. So now did you know what you were going to talk about next week?
I think I'm going to talk about the experiments around Lorenz coming up with his ideas, because poor Lorenz, everyone talks about the Lorenz equations and forgets that his equations really were the basis of relativity and reinvented by Einstein in a lot of ways.
That
Not
sounds
entirely.
Great.
They work together, but
yeah. But there's a bunch of these, so that all sounds great. So so thanks a lot, Pamela.
My pleasure. And we stop our software.
Yeah.
Okay. We're still here. Don't go away. We're just saving. And I'm trying to figure out where my Hangout window is. There it is. So to humor everyone, I host the Google Lunar X Prize team Hangouts, and we had the team from Indonesia on this morning. And if you watch the video on the Google Lunar X Prize Hangouts YouTube page, so go to Google Lunar X Prize on Google+, and then go to the YouTube. It's all far too confusing. Thank you, Google. There is a point during the Hangout where I go like that quite suddenly, because I had never recorded anything at 8 a.m. before, and there was a sunbeam on this wall that freaked the bejesus out of me, because I was just like, where is that? I had no words, and it turned out sunlight apparently will scare me in the morning.
We call that the sun.
Yes.
Terrifying ball of fire. Perhaps we should pray to it as our god.
A cloud moved, the light came out, suddenly the lighting, my camera readjusted to the bright background, and I went dark, and it startled me.
All right, I am uploading my... No, I'm not. Yes, I am. Wait for it. Am I? Yes. Okay, I am uploading my episode. So let's get cracking. Okay. Hugo Blum says, "Hey, Preston, I'm GarageBand Hero, and you have been for so long. Thought you deserved a bit of a shout out." He does.
And I'm copying and pasting that and emailing it to him.
Awesome. This is cool. So James Gibbs says, "Watching here with Rachel Roberts. And we're both very excited that Fraser and Pamela have decided to go with her idea for a mini-series of Astronomy Cast." That's exactly right. Rachel Roberts, this is your idea. We are making this for you.
And it was an awesome idea.
Yeah, great idea. We love it. Nancy Graziano says, "This is the basis of spectroscopy, right? Is that?"
Yes.
I mean, it sort of sounded like beams getting split and interference patterns.
Basis of the Michelson interferometer. The basis of interferometry is just you need a slit. So there's a whole bunch of different work. Brianne Perot, Michelson, a whole bunch of different people worked on what happens when you do weird stuff to light. weird stuff being defined as putting it through lenses, putting it through spaced surfaces, putting it through slits. Many different things were done.
Strange but true, Michelson was a physicist and Edward Morley was a chemist.
Yeah.
It says atom synergy. Let's see. I'm going to try deleting questions or hellos from the Q&A app just so I can...
Sorry, we love you. We just want to find the questions.
Yeah.
And while he's doing that, I'm going to take the time to say, Fraser has a Patreon campaign for Universe Today. CosmoQuest has a Patreon campaign for Learning Space. We have a PayPal account for Astronomy Cast because paperwork. What we do because people like you love us. We love your donations. And more to the point, Learning Space exists strictly on donations as of January 1 because of the restructuring of NASA budgets. And so if you want to say science education matters and NASA may not be releasing any money until sometime next year, but I'm going to release my $1 a month, your $1 a month really goes a long ways.
Yes. Yeah, I mean, if people, when you think about the tens of thousands of people who listen to Astronomy Cast, $1 a month would make a huge difference.
If everyone who downloaded the show donated $1 a month, that would cause us to have a working budget that surpassed all the money I brought in during peak science. There was a year of peak grant money called 2010, and I missed 2010.
Cecil Morgan says, in 1907, Michelson received the Nobel Prize in Physics, became the first American to receive the Nobel Prize in Sciences. So
cool.
There you go. Yeah. Hugo Burnham asks, so what is the difference between ether dragging and frame dragging?
Frame dragging is caused by gravity changing the color of light. Ether dragging is the space across all wavelengths. Gravity affects different colors because they have different energies in different ways. It affects all of it differently by shifting essentially the distance that the light has to travel. So frame dragging, color dependent, ether dragging, not so color dependent.
Ed Thompson says, a science show I watch asks quantum physicists about the possibility of a fourth dimension. Some think there may be as many as 9 dimensions. One even thinks there's really only 1 dimension. Do you think there's a fourth dimension?
It's normally called time.
Sure, but a fourth spatial dimension.
So when you start using words like spatial, it kind of makes my skin start crawling because there's a difference between what we are able to perceive and the totality of reality. A lot of particle physics suddenly makes sense if you start looking at the various aspects as coming from the fact that particles are strings and we can only see the ends of the strings and not the length of them. And if we're looking at the left edge versus the right edge to give a three-dimensional analysis, we perceive them different. So I think the idea of having a many-dimensioned universe where we only perceive the 3 spatial dimensions in time, but there are other dimensions that we aren't capable of perceiving, it makes total sense. Right. More to the point, it suddenly makes particles make sense.
Well, and there was a great explanation of it in the Brian Greene, I think he did a Nova special. It was like a couple of episodes with Brian Greene, and they just they show different ways of imagining a dimension of extra dimensions, that how they could be curled up inside the dimensions as we see them. So the best way to describe is you imagine a piece of string with an ant crawling along the piece of string, and then you think, well, that's just one dimension. But if you sort of scale up the string, the ant might be able to actually go, say, around the string, and so now you've added a second dimension to something that previously was considered only one dimension.
Yes. So, and the idea of multiple dimensions, this doesn't require string theory. It can be gotten to in multiple different explanations. So yeah, I'm totally comfortable with the idea of there being more than 4 dimensions. 1 dimension, no, not comfortable with that. No, I like that theory.
Right, but the idea being that string theory was posited, that once string theory was figured out, that this was a way that you could make gravity and the electromagnetic forces
but they can't
come
actually
together.
get there. I mean, that's the thing, is people postulate a lot about string theory, but they can't create anything that's testable, and they haven't figured out how to actually unite EM and gravity. So I'm in the camp of people who are like, string theory, nice, not nice, actually kind of sucky mathematics. No.
Yeah.
Come back to me with an experiment.
Oh, sure, but I mean, all it was that people got so crazy about multiple additional dimensions because it required those additional dimensions to make the math work at all. So, right, and so like the math comes together if you happen to have 10 dimensions. And
there's non-string theory particle physics that requires multiple dimensions. Multiple dimensions is not unique to string theory, and if it were, string theory might be a little bit more testable. It's not. It's currently really in the category of a belief system.
Right. And one of the other things that I think is really important is, we imagine the expanding universe as a 2-dimensional surface, and you've got all these ants crawling around the 2D surface, and the balloon is expanding, and the ants are seeing the other ants move away from them, and that's the way we always describe the expanding universe. And people go, yeah, but it's a balloon, and you can see where the middle of the balloon is. And where well, yeah, because you're a 3-dimensional creature, and you can see that. But from the perspective of a 2-dimensional creature, you can't. But the point being, we then scale things up, and we're like, we look at the universe, and we can't, the universe is expanding from everywhere. If you were a 4-dimensional creature, you could look at the universe and go, the universe started expanding right there. That's where the Big Bang happened, because I'm a 4D creature and I'm a jerk. So, you're
a 4D creature. You mean a 5D creature?
Yeah, no. If you're a 4D creature, you're the jerk. 5D creatures, they're pretty cool. 11D creatures. We did this in one of our latest videos.
Understand spin theory better.
We actually went through this on one of our latest videos. We talked about where the center of the universe, center of the universe is, and where the Big Bang happened, and talked about how as you go up essentially the personalities of the different dimensional creatures as you move up the scale. So we talked about how, sure, 4D creatures know where the center of the universe is because they're cool like that. But the 5D creatures, they'll just lord over this knowledge. Yeah. Anyway, you should watch our episode. It's pretty funny. Actually, I'm really happy. Boy, our latest one about our astronauts weightless is by far my favorite episode we've ever done. It was so much fun.
That's cool.
Yeah. We found the exact right video footage from NASA to go along with the ridiculous things that I was saying. So it's wonderful. All right, we got a few more minutes. Let's keep rolling. All right. So Nancy Graziano asks, is it possible that dark matter comprises the medium through which light travels? Since we have not discovered what dark matter is, could it mask itself enough that it would appear that light required no transmission medium when in fact it uses dark matter?
Nope.
Okay.
So the issue is that dark matter clearly clumps because we can see how it bends light, and dark matter only interacts via gravity. Light is the electromagnetic force. It's the boson that communicates the electromagnetic force. So since dark matter ignores the electromagnetic force, it's not to blame. But the mass that dark matter has can be seen to bend light because light gets bent by gravity. And we can clearly see that dark matter has these clumpiness to it. There's some amazing images of the dark matter distribution associated with merging galaxy clusters. And the Cosmos Project actually came out with a detailed map of dark matter over multiple epochs.
Did you hear that they've discovered, it looks like they found evidence for dark matter galaxies?
I'm still waiting for deeper, darker imagery.
Yeah, so they found galaxies that have nothing but dark matter in them.
I'm kind of uncomfortable with the word galaxy instead of saying overdensities. Saying that they found, because galaxy implies star, supermassive black hole, all of this stuff and structure, and the 1 over r to the alpha value for how it falls off with distance. And if it's pure dark matter, none of those things are there. So finding dark matter halos without luminous components, I'm good with. But saying dark matter galaxies, really kind of a misconception leading phrase.
Well, we'll be interviewing the lead researcher shortly on the Weekly Space Hangout, so I will pass along your concerns. Or feel free to show up.
When are you doing that?
In March.
Okay, I'll try and show up. I'm starting to free up my schedule. Well, no, actually, NASA is freeing up my schedule. So
we had astronaut Ron Guerin 2 weeks ago.
Rubbing that in, and more to the point, you had Andy Weir, who's more exciting.
Yeah, and we got even cooler guests coming up. So, well, it's hard to beat those two. Equivalently cool guests coming up. We're definitely shooting high. We're putting everyone on our wish list, and we're cranking it out. Huge thanks to Nancy Graziano and a bunch of the people who are in the chat right now. Hugo Burnham and
you guys are awesome.
They're all helping out. They've been really pitching in to get their guest. My feeling about the Weekly Space Hangout is that it's just for the folks who love the show, and I can be the moderator for whoever they want to talk to. I will be their avatar in this world. So, and apply whatever gravitas I can bring to an influence and reputation to let them hear whoever they want to hear talk about stuff they want to talk about and pass along their questions. So, anyway, go to the if you haven't already, go to Google+, go to the WSH Crew community on Google+. And this is sort of the core community of people who are mostly helping out with the Weekly Space Hangout, and by all means jump in and talk to them about space and what they want to see in the upcoming show. Okay, let's move on. So Hugo Burnham notes that the Large Hadron Collider may confirm quantum gravity this year. Big maybe. What's quantum gravity, Pamela?
No.
Okay. Maybe we'll do that as a future episode. What do I want to talk about now? Okay, Richard Clark asks, if NASA had the same funding as the current military budget, could the possibility of having a space station and a base on the moon similar to 2001, a space odyssey, be realized within 10 years? Would the new mining, manufacturing, technology developed help fund this? Look, I'm out of focus.
I just learned that we have an Astronomy Cast Patreon.
Yeah, I know.
I didn't.
Yeah, I'm not sure where it came from and who set it up, but it exists.
That's deeply confusing and somewhat disturbing.
Someone should dig into that. Okay, so if NASA had the same funding budget as the military budget, could they have a space station and a base on the moon? And how, I think, would be the way I would describe that. I mean, like, what's the U.S. military budget? $500 billion a year?
The have it within 10 years is because of the ramp-up time, but had the NASA budget consistently been equal to the U.S. military budget, is that too much to ask for? Then, yeah, we'd be on Europa being cast out by now.
Yeah. Yeah, well, hold on. What's the U.S. military budget?
A lot.
$610 billion in 2015. No, 2013. So NASA's budget's about what, 17 million, 18 billion. So maybe 20. Let's call it a nice round number. Call it 20 billion. So that's a lot.
Yeah.
30 times the current space exploration budget. So I'm going to say yes. We would have started now, spent that kind of money with the technology that we have, with partnerships with SpaceX. Absolutely, we would be multiple bases on the moon. We would be humans on their way to Mars, as you said, bases on Europa. We would be. New Horizons was what, like a $300 million mission? It was
It was basically free compared to like a bomber.
Yeah.
One of the things that I really want to do, except I don't have time, but someone out there might, is put together a this is what this costs the military, this is what this costs in space.
Well, we were in we went to the Boeing field in Everett, and they were talking about the 747s, U-747s, and what they cost.
Yeah.
I don't remember the price. $65 million, I think, but maybe that was just for a 737. Anyway, crazy expensive. Yeah, I wrote an article. We put an article on Universe Today a couple of days ago. It was pretty controversial. The gist being, the title that I picked was, "Here's a good use for fighter jets launching satellites." So they've figured out, DARPA is working on how to make fighter jets into launch platforms for satellites. So, like a Minotaur, right? You put the rocket underneath the fighter jet. It takes off, flies up, gets a good trajectory, and then the rocket detaches and flies off into space. And so you could theoretically launch rockets for a fraction of the price for what you would do for some of these smaller, small like CubeSat loads, things like that. And so I'm thinking, like, instead of having these things kill people, let's have these things launch satellites. I think that's just great. Okay.
Sorry, this is me typing to find out who owns the Patreon for Astronomy Cast, that I just saw someone.
We will dig that perhaps after the show.
Yeah, sorry, typing because I'm having the internal panic that comes from seeing. I love all of you out there, and I don't donate to the Astronomy Cast Patreon, donate to Universe Today or Learning Space until we figure this out.
Yeah. And so the Universe Today is patreon.com/Universe Today, and you'll see the one that's up to close to $1,800. So.
Yeah, Learning Space is like $50. So
we've been doing it for about a year.
Please give to Learning Space. We're only a couple of weeks old, and we're $94 a month. As you know from us canceling several episodes, I've been fighting the intestinal gods for the past couple of months, so I haven't put the energy into promoting it. So if you can, you don't have to give. If you can promote the Learning Space Patreon campaign, that would be huge. We're just trying to get astronomy education out there. Okay, I'm going to shut up now.
Okay, Steve Eskison asks, okay, here you go. I want to create a new habitable planet in our solar system. I have no budget constraints and 100 million years. My plan, crash Mars, Venus, and Europa into each other with enough precision to have a roughly 24-hour day and moons. Viable?
It depends on how many moons you create. The issue is, if the mass of the body itself is too high, you and your 24-hour day are going to have one heck of a dense atmosphere, and it's going to be rather unpleasant. Now, the nice thing about the combination of worlds that you're colliding is you've got all of the materials you want.
Yeah.
Lots of water. So you're good to go, but I'm honestly not quite sure why you do this when you could instead just, like, if you combined Mars and Europa, you're still not quite big enough to be happy. Mm-hmm. But if you could, like, build Mars up to be big enough to hold on to its atmosphere, leave Earth alone. Venus,
you're not crushing Earth. You're not crushing Earth.
Sorry. That's where I went on to. Leave Venus where it is.
No way. Venus. Venus needs to be pushed into the sun. Like this is a better idea than what we've got Venus doing right now, which is just being a horrible hellscape.
You're
It's got
gonna
sulfuric acid rain.
you're
Venus is
gonna
dead to me.
destroy Venus because you can?
Should, must. So I think Steve's plan is legit. I think the only issue is where you do it, right? Like let's think of the future. He's got the time frame. The sun is heating up. So let's get it further away from the sun, and we'll call that like Earth 2. Nice stable orbit somewhere around the orbit of Mars, and then
Really bad TV show.
Yeah, and then as the sun makes Earth unlivable, we move to Earth 2, which is settle down after you've crashed all these planets together.
Okay. I think we just need to take what you're talking about and put it happily in orbit of Jupiter. I mean, so something I don't know, and now I want to go find out. This is probably a Wolfram Alpha question, but I won't do it on air. Is what is the combined mass of all of Jupiter's Trojan asteroids and its moons? Could we get a halfway reasonable surface gravity by combining all of the rocky stuff near Jupiter into one?
Well, let's call that Earth 3, which after Earth 2 becomes unlivable. Okay, that's where we'll go next, and then we'll just take the entire Kuiper Belt and mash it into something.
But if you put Earth 3 in the right orbit of Jupiter with Mars, let's take Mars out there for moving Mars, you can get this nice tidal dynamics going on with the two of them, so that when they're going in and out of resonance, think Galilean moons, you can start getting some tidal heating going. You might even just be able to get away with just one of them without moving Mars, just the right elliptical orbit, and figure out how to make it so that it doesn't circularize over time. So a nice elliptical orbit, tidal forces, heating.
Yep.
You're good. You're good right now. If there's
Awesome.
enough mass. I don't know if there is.
All right. Well, you know what? It's 2:00. We've been at it for an hour. Let's wrap this up.
Okay.
So thank you, Pamela.
Thank you.
And we will return next week. I am flying to Vancouver. Yeah, I'll be able to make it. Be tight. Okay. Can't go any later. We have to record Monday at noon.
Okay.
Okay. All right. Thanks, everyone. We will see you all next week.
Bye-bye.